On May 1, 1960, Soviet Premier Nikita Khrushchev stood before the world and declared, "We will shoot down any aircraft that violates our airspace. Our missiles can reach any altitude. Our radars see everything. There is no place to hide." The laughter began that afternoon. Not literal laughter, but the institutional smugness of a military establishment that believed it had solved aerial warfare forever. Soviet air defense commanders updated their doctrine manuals. Training programs emphasized the inevitable mathematics of interception. The sky, they declared, belonged to the defense. Khrushchev was wrong. Within 7 years, American reconnaissance aircraft would penetrate the most heavily defended airspace in human history. They would fly over Moscow itself. They would photograph nuclear installations, missile sites, and strategic facilities, while Soviet defenders fired hundreds of missiles and achieved exactly 0 successful intercepts. These aircraft didn't hide from enemy defenses. They didn't evade enemy weapons. They simply flew so fast that physics itself made interception impossible. At Mach 3.2 and 85,000 feet, they existed in a flight regime where even perfect detection meant nothing, where flawless coordination was irrelevant, where overwhelming firepower arrived too late to matter. This is the story of how American engineering silenced Soviet laughter forever. This is the story of the machine that made time itself a weapon. This is the story of total annihilation through absolute speed. On May 1, 1960, at precisely 11:37 Moscow time, a Soviet SA-2 surface-to-air missile climbed through 35,000 feet of clear spring air and detonated its warhead beneath the belly of a Lockheed U-2 reconnaissance aircraft. The pilot, Francis Gary Powers, descended under parachute into the hands of the KGB, and in the Kremlin, Premier Nikita Khrushchev permitted himself what would prove to be the most catastrophic smile in the history of military aviation. Within hours, Soviet radio was broadcasting the news to the world. The voice was steady, confident, almost bored with its own triumph. "The aggressive aircraft of the United States has been shot down," came the announcement. "Our anti-aircraft defenses have proven that the sky above the Soviet Union is not open territory for American spies." But it was Khrushchev himself who delivered the verdict that would echo through the corridors of the Pentagon and the classified briefing rooms of Langley for years to come. Standing before the Supreme Soviet, his voice rising with each syllable, he declared, "We will shoot down any aircraft that violates our airspace. The era of American impunity is over. Our missiles can reach any altitude. Our radars see everything. There is no place to hide." The laughter began that afternoon. Not literal laughter, but the institutional smugness of a military establishment that believed it had solved the fundamental equation of aerial warfare. Soviet air defense commanders updated their doctrine manuals. Training programs emphasized the inevitable mathematics of interception. Missile batteries proliferated across the vast expanse of the USSR like mechanical flowers blooming in deadly gardens. The Americans, meanwhile, sat in their sterile conference rooms and confronted a mathematics problem that threatened to reshape the entire Cold War. The U-2 had been their answer to the closed society of the Soviet Union. Flying at 70,000 feet, it had sailed serenely above the reach of interceptor aircraft, photographing missile sites and military installations with impunity. Now that sanctuary was gone, destroyed by a missile that had climbed higher than any fighter could fly. In the immediate aftermath of Power's capture, CIA reconnaissance requirements officers gathered around tables covered with maps and charts, their faces grim with the recognition of what they had lost. The intelligence gaps over denied territory had suddenly become chasms. Satellite technology existed only in theoretical form, years away from operational deployment. The revisit rate mathematics were brutal. A single satellite orbit meant waiting days or weeks for another glimpse of the same target, while Soviet missile deployments could be completed in hours. The enemy had closed the sky, and America needed a new way to see. Colonel Jack Ledford, speaking to a closed session of the Defense Intelligence Agency, put it with characteristic bluntness. "Gentlemen, we are flying blind over a nuclear-armed adversary. Every missile site we cannot photograph, every airfield we cannot monitor, every submarine base we cannot assess, represents a potential first strike capability that could end civilization as we know it. The U-2 was not just an aircraft, it was our early warning system. Without it, we are reduced to guessing about Soviet intentions, and in nuclear warfare, guessing is another word for suicide." The mood in Moscow, by contrast, was one of vindicated confidence. Marshal Sergei Biryuzov, commander of Soviet air defense forces, held press conferences where he explained the technical superiority of Soviet missile systems. The SA-2 guideline, he declared, could engage targets at altitudes up to 80,000 feet and at ranges exceeding 25 miles. More importantly, the radar systems guiding these missiles had demonstrated their ability to track high-altitude targets from detection to destruction. But it was the mathematics that seemed most convincing to Soviet planners. A reconnaissance aircraft, no matter how high it flew, was still subject to the laws of physics. It required time to cross Soviet airspace, time measured in hours. The SA-2 missile, once launched, could reach maximum altitude in under 2 minutes. The mathematics appeared overwhelming. Hours of vulnerability against minutes of response time. The equation seemed to favor the defender absolutely. Soviet technical journals published detailed analyses of the intercept geometry. Radar cueing systems had demonstrated their ability to hand off tracking data to missile batteries with minimal delay. Command and control networks could coordinate multiple launches against a single target. The bottlenecks that had historically plagued air defense systems, communication delays, target handoff failures, coordination breakdowns, had been systematically eliminated through rigorous training and technological improvement. The doctrine that emerged from this confidence was elegantly simple. The sky was defensible. Any aircraft that attempted to penetrate Soviet airspace would be detected, tracked, and destroyed. Altitude was no longer a sanctuary. Speed, within the realm of existing aircraft, provided no meaningful protection against missiles that flew at 3 times the speed of sound. Yet even as Soviet planners celebrated their technological triumph, American engineers were already confronting a different set of mathematics. In classified facilities scattered across the American aerospace industry, teams of designers and physicists were examining the fundamental assumptions underlying air defense systems. They were asking questions that the Soviets, in their confidence, had not yet considered. The first question was simple but profound. What if altitude was not enough? What if the answer was not to fly higher, but to fly faster? Fast enough that even detection would not provide sufficient time for successful interception. Dr. Eugene Kincaid, writing in a classified RAND Corporation study dated June 1960, outlined the theoretical possibility. Current Soviet air defense doctrine assumes sufficient time between detection and weapon release to complete a successful intercept. This assumption is based on the flight characteristics of existing reconnaissance aircraft. However, if target speed were increased dramatically beyond the performance envelope of current systems, time available for successful intercept could be reduced to the point where even perfect detection would not guarantee successful engagement. The mathematics were brutally simple. A missile fired at an aircraft traveling at 600 miles per hour had minutes to complete its intercept. But an aircraft traveling at 1,800 miles per hour, 3 times the speed of sound, compressed those same engagement windows into seconds. And seconds, as any air defense commander understood, represented the difference between theoretical possibility and operational reality. The CIA's reconnaissance requirements, circulated in classified memoranda throughout the summer of 1960, made the desperation explicit. Intelligence analysts needed to monitor Soviet missile deployments in real time. Submarine construction schedules had to be tracked continuously. Nuclear weapons testing facilities required constant surveillance. The gaps in intelligence collection were not merely inconvenient, represented potential strategic surprise on a scale that could determine the outcome of the Cold War. But the requirements seemed to violate the laws of physics. The aircraft would need to fly higher than any interceptor could reach, faster than any missile could follow, and with sufficient range to traverse the enormous expanse of Soviet territory. It would need to operate in temperature extremes that would destroy conventional aircraft, at altitudes where the atmosphere was so thin that conventional engines would fail, and at speeds where aerodynamic heating would melt traditional airframe materials. The impossible brief was becoming more impossible with each requirement added to the list. Meanwhile, in Moscow, Khrushchev was discovering that confidence was a commodity that could be exported. Speaking to delegations from Warsaw Pact nations, he outlined the new reality of aerial warfare. Soviet air defense technology, he explained, had fundamentally altered the balance of power. No longer could Western powers rely on technological superiority to penetrate socialist airspace. The era of aerial reconnaissance was ending, to be replaced by the certainty of mutual deterrence through defensive invulnerability. The propaganda value was enormous. Soviet military journals published detailed technical specifications of the SA-2 system, demonstrating to the world that socialist technology had achieved parity with and superiority over capitalist military systems. The shoot-down of the U-2 was presented not as a lucky hit, but as the inevitable result of scientific socialism applied to military engineering. But beneath the propaganda, Soviet engineers were making assumptions that would prove catastrophic. They assumed that aircraft technology would evolve incrementally. They assumed that speed and altitude improvements would follow predictable curves. Most fatally, they assumed that the mathematics of interception would remain constant, that there would always be sufficient time between detection and engagement to complete a successful attack. Colonel General Ivan Tretyak, commander of the Moscow Air Defense District, expressed this confidence in terms that would later seem prophetic in their irony. The laws of physics do not change to accommodate capitalist wishes. Our missiles fly at Mach 3. Our radars can track targets beyond the horizon. Our command systems can coordinate hundreds of simultaneous engagements. There is no aircraft that can fly fast enough to escape this network. The sky belongs to the defense. The Americans, however, were beginning to understand that the laws of physics cut both ways. In a series of classified briefings held throughout the late summer of 1960, aerospace engineers presented calculations that challenged every assumption underlying air defense doctrine. They demonstrated that speed, pushed to its absolute limits, could collapse engagement timelines to the point where even perfect defensive systems would fail. The key insight was elegantly simple. Air defense systems were optimized for aircraft that behaved predictably. They assumed targets that flew straight lines at constant speeds, that provided sufficient warning time for radar operators to assess threats and coordinate responses, that remained within engagement envelopes long enough for multiple shots. But an aircraft that flew fast enough could violate all of these assumptions simultaneously. Dr. Clarence Johnson, chief designer at Lockheed's Advanced Development Projects facility, outlined the theoretical possibility in a presentation to CIA and Air Force officials. Gentlemen, we are not discussing incremental improvements to existing aircraft. We are discussing a fundamental redefinition of what an aircraft can be. Speed is not just about going faster. Speed is about denying time itself. The concept was revolutionary. Instead of trying to hide from enemy defenses, the aircraft would deny them the time necessary to respond. Instead of flying higher to avoid missiles, it would fly so fast that missiles could not reach it before it had moved beyond their engagement envelope. Instead of relying on stealth or deception, it would rely on the absolute certainty of physics. That even light-speed communications and instantaneous responses could not compensate for insufficient time. But transforming theoretical possibility into operational reality would require solving engineering problems that had never been solved before. The aircraft would need engines that could operate efficiently at 3 times the speed of sound. It would need an airframe that could withstand temperatures exceeding 1,000 degrees Fahrenheit. It would need fuel systems that could function as cooling systems, navigation equipment that could operate in the thin atmosphere above 80,000 feet, and pilots capable of flying a machine that existed at the very edge of what was physically possible. The Soviet response to these theoretical possibilities was dismissive. Marshal Beryuzov, in a speech to the Warsaw Pact Defense Ministers' Conference, outlined the mathematical impossibility of the American approach. Our calculations demonstrate that any aircraft attempting to fly at such speeds would destroy itself through thermal stress before it could complete a reconnaissance mission. The Americans are chasing fantasies. Physics is not subject to political pressure. But even as Soviet confidence hardened into doctrine, American industry was mobilizing resources on a scale unprecedented in peacetime. The impossible brief was becoming a national priority, backed by funding that treated engineering challenges as problems to be solved rather than limitations to be accepted. Speed, the Americans were beginning to understand, was not just about velocity. It was about rewriting the fundamental equations of aerial warfare. It was about transforming time itself from an ally of the defense into a weapon of the offense. It was about making the enemy's confidence irrelevant by making their weapons arrive too late to matter. The laughter in Moscow was about to die. And in the classified workshops of American aerospace companies, the future was taking shape in the form of blueprints and equations that would prove Marshal Beryuzov's confidence to be the most expensive mistake in the history of air defense. The machine that would make Soviet boasts meaningless was already being born, crafted by engineers who understood that sometimes the impossible was simply another word for inevitable. The sky was about to change hands, and this time it would not be through superior firepower or better tactics. It would be through the ruthless application of physics to the problem of denying time itself. In the winter of 1960, as snow fell across the classified facilities of Burbank, California, a different kind of warfare was beginning. This was not the warfare of missiles and radar, but of metallurgy and thermodynamics.
of supply chains and production schedules. The battle for the sky would be won or lost, not in the stratosphere, but in the machine shops and wind tunnels where the impossible was being hammered into reality. At Lockheed's Advanced Development Projects facility, known simply as the Skunk Works, the morning of December 15th began with a security briefing that would have seemed absurd to any rational observer. Engineers arriving for work were reminded that the project they were about to join did not officially exist. The aircraft they would design had no designation, no budget line, and no public acknowledgement. Even its existence was classified at levels that required special clearance to discuss. Clarence L. Kelly Johnson stood before a gathering of engineers, mathematicians, and metallurgists, his voice carrying the weight of absolute authority. "Gentlemen," he began, "we are about to attempt something that every textbook says is impossible. We are going to build an aircraft that flies at Mach 3.2 for hours at a time, at altitudes above 85,000 feet, over distances exceeding 3,000 miles. We are going to do this with materials that barely exist, engines that have never been tested, and fuel that has yet to be invented. And we are going to do it in less than 4 years." The silence that followed was broken only by the sound of pencils scratching on paper, as engineers began calculating the magnitude of what they were being asked to accomplish. The thermal loads alone seemed prohibitive. At Mach 3.2, aerodynamic heating would raise the aircraft's skin temperature to over 600 degrees Fahrenheit. At such temperatures, aluminum would lose its structural integrity. Steel would expand beyond acceptable tolerances. Even titanium, the wonder metal of the aerospace age, would be pushed to its absolute limits. But Johnson had built his career on transforming impossible requirements into operational aircraft. The U-2 had been considered impossible when its development began. The F-104 starfighter had violated every conventional wisdom about high-speed flight. Now, he was being asked to do it again, but on a scale that dwarfed every previous achievement. "The first rule," Johnson continued, "is that we will not attempt to solve every problem at once. We will divide this aircraft into systems, and we will solve each system completely before moving to the next. The engine team will focus solely on making the J-58 work at sustained Mach 3. The structures team will focus solely on building an airframe that can withstand the thermal environment. The fuel team will focus solely on developing a coolant that can also power the aircraft. No one worries about anyone else's problems until their own problems are solved." This was Kelly's law in action. The systematic decomposition of impossible problems into merely difficult ones. But even the difficult problems were stretching the boundaries of known science. Engine, for instance, was not really a single engine, but a hybrid system that would transform itself in flight. At takeoff and low speeds, the Pratt & Whitney J-58 would operate as a conventional turbojet. But as speed increased beyond Mach 2.5, bypass doors would open and the engine would begin functioning more like a ramjet, with the turbojet serving mainly to pump air through combustion chambers that were, in effect, controlled explosions contained within carefully designed metal chambers. Test stand logs from the winter of 1961 recorded the brutal reality of this transformation. Engine number 1001 completed 17 minutes of Mach 3+ operation before critical components began reaching temperature limits. Engine 1002 lasted 23 minutes before thermal expansion caused catastrophic failure. Engine 1003 incorporated redesigned cooling passages and managed 41 minutes of sustained operation before metallurgical limits were exceeded. Each failure provided data. Each data point refined the design. Each refinement brought the team closer to an engine that could operate reliably in an environment that no engine had ever been asked to survive. Ben Rich, Johnson's deputy and the man who would later succeed him as head of the Skunk Works, described the methodical brutality of the development process. We were not building an aircraft. We were building a flying laboratory for testing the limits of what was physically possible. Every component was being pushed beyond anything that had been tried before. The engine had to work in an environment hot enough to melt lead. The fuel system had to function as a cooling system while remaining combustible enough to power the aircraft. The airframe had to expand and contract by inches during each flight, while maintaining structural integrity sufficient to support 50,000 pounds of aircraft at 3 times the speed of sound. The titanium problem exemplified the challenges they faced. The aircraft would be constructed of 85% titanium, a metal so difficult to work with that conventional manufacturing techniques were useless. Titanium could not be welded using traditional methods. It could not be machined using steel tools. It could not be formed using conventional presses. Every manufacturing process had to be invented from scratch. Procurement cables from this period read like dispatches from an industrial war. Require 40,000 pounds titanium sheet. Minimum purity 99.2%. Delivery schedule critical. Welding environment must maintain argon purity below 20 parts per million oxygen. Tool steel insufficient for titanium machining. Require carbide tooling for all forming operations. The supply chain became a battlefield unto itself. The Soviet Union, ironically, produced some of the world's highest quality titanium. American procurement officers found themselves purchasing Soviet titanium through third-party suppliers, a process that added months to delivery schedules and thousands of dollars to material costs. The CIA established shell companies to purchase strategic materials without revealing their ultimate destination. But the most complex challenge was not mechanical, but chemical. The fuel that would power this aircraft did not exist. Conventional jet fuel would vaporize at the temperatures the aircraft would experience. The fuel system would need to circulate the fuel throughout the aircraft as a coolant before burning it in the engines. This meant developing a fuel that could absorb enormous amounts of heat while remaining stable enough to combust efficiently. Shell Oil Company's chemical engineering division received a specification that seemed to violate basic chemistry. The fuel needed a flash point above 140 degrees Fahrenheit to prevent vaporization in the fuel tanks, but it also needed to ignite reliably at the extreme conditions inside the engine combustion chambers. It needed to remain liquid at temperatures that would boil water, while serving as an effective coolant for aircraft systems, generating heat loads equivalent to a small power plant. Dr. Robert Abernethy, Shell's chief fuel chemist, later recalled the challenge. They were asking us to develop a fluid that would function as hydraulic fluid, cooling fluid, and combustible fuel simultaneously. The thermal properties had to remain stable across a temperature range from -40 degrees at altitude to +600 degrees in the fuel lines. The chemistry involved was unlike anything we had attempted before. The solution, designated JP7, required 18 months of development and represented a fundamental breakthrough in fuel chemistry. Unlike conventional jet fuel, JP7 was virtually impossible to ignite accidentally. A lit cigarette dropped into a pool of JP7 would extinguish itself, but under the precise temperature and pressure conditions inside the J58 engine, It would burn with the controlled ferocity necessary to sustain Mach 3+ flight. Production logs from the Lockheed facility during 1964 reveal the methodical precision with which the impossible was being made routine. Tolerance measurements were recorded in thousands of inches. Temperature specifications were maintained within 2 degrees Fahrenheit. Surface finishes were measured in micro-inches. Quality control inspectors rejected components for imperfections invisible to the naked eye, but potentially catastrophic at 3 times the speed of sound. The aircraft taking shape in these facilities was designated the A-12, though it would later be known to the public as the SR-71 Blackbird. But in 1964, it existed only as components that seemed to defy rational explanation. Wing sections constructed entirely of titanium, engine inlets designed to function as supersonic diffusers, fuel tanks that served as structural elements while containing fluid at temperatures that would cook conventional aircraft. Each aircraft required 15,000 individual parts, manufactured to tolerances that precision. Instrument manufacturers would have considered excessive. A single wing section required 1,247 titanium components, each machined to specifications measured in fractions of millimeters. The landing gear assemblies alone weighed more than entire fighter aircraft, yet had to retract into spaces designed with the precision of Swiss watchmaking. Lou Schalk, Lockheed's chief test pilot, documented the surreal nature of his workplace. "We were test flying an aircraft that officially did not exist, using fuel that was not available to the public, at speeds that no aircraft had ever sustained, at altitudes where the sky was black and the Earth's curvature was clearly visible." The test flights themselves were classified at levels that required special briefings just to discuss weather conditions. The first A-12 flight on April 26, 1962, lasted exactly 17 minutes and reached a maximum speed of Mach 1.1. By conventional standards, it was unremarkable. But the engineers watching from the ground understood that they had just witnessed the birth of a machine that would redefine the physics of aerial warfare. The production schedule that followed was unlike anything attempted in peacetime. 32 aircraft would be manufactured, each one a hand-built precision instrument requiring 6 months of assembly time. Components were manufactured in facilities scattered across the United States, then shipped to Burbank for final assembly under security conditions that treated each aircraft as a national strategic asset. The financial ledgers tell their own story. Each aircraft cost approximately $34 million in 1964 dollars, equivalent to over $250 million in modern currency. But the cost was not measured merely in dollars. Each aircraft represented 150,000 man-hours of labor, 40,000 pounds of titanium, 18,000 precision-machined components, and industrial processes that had been invented specifically for this single application. Quality control required testing, procedures that bordered on the obsessive. Every weld was X-rayed. Every component was stress-tested beyond operational limits. Every system was tested, retested, and tested again under conditions that simulated the extreme environment the aircraft would encounter at the edge of space. The result was not mass production, but precision replication. Each aircraft was essentially a custom-built machine, assembled by technicians who understood that a single manufacturing error could result in catastrophic failure at speeds and altitudes where pilot ejection was impossible. By December 1964, the first operationally configured A-12 completed a flight that lasted 4 hours and 17 minutes, reached Mach 3.29, and climbed to 88,300 feet. The flight was routine in every respect, except one. It had just demonstrated that the impossible was now operational. But the true measure of the Skunk Works achievement was not found in the specifications or performance charts. It was found in the systematic destruction of every assumption that had made Soviet air defense planners confident. The aircraft they had built did not merely fly faster than existing aircraft. It flew so much faster that it existed in a different realm of physics entirely. The machine was complete. The battlefield was about to change. And in Moscow, the laughter was about to become silence. The first operational reconnaissance mission launched from Kadena Air Base in Okinawa on May 21, 1967, at precisely 0347 hours local time. The pilot's name was Dennis Sullivan, though for security purposes he existed in all official records as simply Pilot 1. His target was a suspected missile installation in North Vietnam, and his flight plan called for a route that would take him over some of the most heavily defended airspace in military history. Sullivan's pre-flight briefing had been delivered in a windowless room where classified photographs covered every available wall surface. Soviet SA-2 missile sites dotted the landscape like deadly flowers. Radar installations formed an interlocking network of electronic surveillance. Fighter aircraft stood ready on airfields that could launch interceptors within minutes of detection. The briefing officer's final words were matter-of-fact. "Gentlemen, you will be flying over the most sophisticated air defense network ever deployed in combat. They will see you coming. They will track you continuously. They will fire everything they have. Your survival depends entirely on speed." The aircraft that Sullivan climbed into that morning bore only a passing resemblance to conventional reconnaissance aircraft. The A-12, painted in a blue-black finish that seemed to absorb light itself, stretched 102 feet from nose to tail and weighed 127,000 pounds when fully fueled. But statistics could not capture the alien nature of the machine. It looked like something that belonged in space rather than in the atmosphere, a product of engineering disciplines that had pushed the boundaries of known science. At precisely 0400 hours, Sullivan advanced the throttles and began his takeoff roll. The J-58 engines, spooling up to full power, produced a sound unlike anything in aviation. It was not the scream of conventional jets, but a deeper rumble that seemed to originate from the aircraft's core and radiate through the ground itself. Observers reported feeling the sound as much as hearing it, a physical force that announced the presence of something fundamentally different. The aircraft rotated at 207 knots and climbed at an angle that defied conventional understanding of aerodynamics. Within 4 minutes of takeoff, Sullivan was passing through 30,000 feet and still accelerating. By the time he crossed the coastline of Vietnam, he was approaching Mach 2 and climbing through 60,000 feet. The enemy's most sophisticated radar systems detected him immediately, but the information they provided was unlike anything their operators had encountered before. Senior Lieutenant Yuri Volkov, manning a Soviet-supplied early warning radar station outside Hanoi, later described the moment of detection. "The target appeared on our screens at maximum detection range, traveling at a speed that our equipment initially rejected as a malfunction. We recalibrated our systems twice before accepting that we were tracking an aircraft moving at over 2,000 kilometers per hour. But speed was only the beginning of the problem. The target was climbing continuously, passing through altitudes where our missiles could not follow. The mathematics of interception, so favorable to Soviet planners in 1960, were collapsing in real time. The SA-2 missile required approximately 90 seconds to reach maximum altitude and 35 seconds to arm its proximity fuse. But Sullivan's aircraft was crossing the engagement envelope faster than the missiles could reach intercept altitude. By the time a missile launched from the outer edge of its engagement zone could reach 70,000 feet, Sullivan was already 40 miles downrange and climbing through 80,000 feet. The first missile launch came at 0447 hours, fired from a battery north of Hanoi at maximum range. The radar operator achieved a clean lock and maintained track continuity throughout the engagement. The missile's trajectory was textbook perfect, arcing upward toward an intercept point calculated by computers that had never failed to provide a solution. But as the missile reached apogee, the target was no longer there. Sullivan had simply outrun the geometry of interception. Mission recordings from Sullivan's cockpit reveal the surreal calm of a pilot operating in an environment where conventional threats had become irrelevant. Passing flight level 800, Mach 3.1 and climbing. Multiple launches observed, but no proximity warnings. Systems are green across the board. Beginning photo run in 30 seconds. At 85,000 feet and Mach 3.2, Sullivan was flying in an environment that existed at the very edge of the atmosphere. Outside his cockpit windows, the sky was black as space, and the curvature of the Earth was clearly visible. His engines were operating in air so thin that conventional turbojets would have flamed out instantly. But the J-58s, functioning now primarily as ramjets, were extracting energy from the supersonic airflow with an efficiency that increased with speed. The camera systems that recorded the mission operated with a precision that redefined reconnaissance photography. From 85,000 feet, the cameras could resolve objects 18 inches in diameter. Missile sites were photographed with such clarity that individual launch rails could be counted. Vehicle movements were tracked with temporal resolution measured in seconds. The intelligence product from a single overflight exceeded everything that months of conventional reconnaissance had achieved. But from the perspective of the defenders, the mission represented something approaching technological humiliation. Colonel Tran Van Minh, commander of the North Vietnamese 261st Air Defense Regiment, filed a report that captured the frustration of his situation. The enemy aircraft penetrated our airspace at will, photographed our most sensitive installations with impunity, and departed without sustaining damage despite the expenditure of 14 surface-to-air missiles. Our radar systems functioned perfectly. Our missile guidance was accurate. Our crews performed their duties flawlessly, but the target was simply too fast for successful engagement. The missile launches that followed Sullivan's penetration became increasingly desperate. Batteries fired at maximum range, hoping to achieve lucky hits rather than calculated intercepts. Proximity fuses were adjusted to detonate earlier, creating larger fragmentation patterns that might catch an aircraft moving too fast for precise targeting. Multiple batteries coordinated simultaneous launches, attempting to saturate the airspace ahead of the target's projected flight path. Nothing worked. The mathematics were immutable. An aircraft traveling at Mach 3.2 at 85,000 feet existed in a flight regime where conventional air defenses were not merely ineffective, but fundamentally irrelevant. The missiles were still climbing toward their intercept altitude when the target had already exited their engagement envelope. Flight Lieutenant Nguyen Van Duc, piloting a MiG-21 interceptor, attempted the only fighter intercept of the mission. His aircraft, capable of climbing to 60,000 feet at maximum performance, managed to reach 57,000 feet before fuel limitations forced him to abandon the intercept. His post-flight report was concise. Visual contact was never achieved. Target altitude and speed were beyond the performance envelope of available interceptor aircraft. The intelligence collected during Sullivan's 4-hour mission filled 11,000 feet of film, and provided the most comprehensive assessment of North Vietnamese air defenses ever achieved. But beyond the immediate intelligence value, the mission had demonstrated something that would reshape military planning for decades. Speed, pushed to its absolute limits, could render even the most sophisticated defenses powerless. Soviet technical advisors in Hanoi filed their own reports, and the language was notably different from the confidence that had characterized their assessments in 1960. Colonel Alexei Kuznetsov, senior air defense advisor, wrote, "The American reconnaissance aircraft operates in a flight regime that appears to be beyond the engagement envelope of current surface-to-air missile systems. Radar detection and tracking present no difficulties, but target speed and altitude combine to create intercept geometry problems that may be fundamentally unsolvable with existing technology." The word unsolvable appeared in classified Soviet communications for the first time since the U-2 shootdown. But unsolvable was precisely what American engineers had intended. They had not built a better airplane. They had built an airplane that operated according to different physical laws. As Sullivan descended through 50,000 feet on his return flight to Kadena, Soviet radar operators tracked his progress with the same precision they had maintained throughout the mission. Every missile battery remained at highest alert. Fighter aircraft continued to orbit at maximum altitude, ready to attempt intercepts that their crews knew were impossible. The entire air defense network functioned exactly as designed, with one catastrophic exception. Nothing they did mattered. The mission logs recorded the expenditure of 16 surface-to-air missiles, 847 rounds of anti-aircraft artillery, and 23,000 gallons of fighter aircraft fuel. The enemy had responded with overwhelming force, perfect coordination, and flawless execution of established procedures. The final score was simple. Dozens of missiles launched, 0 hits achieved. But the true impact of the mission was measured not in missiles expended, but in confidence destroyed. Soviet air defense doctrine, built on 7 years of systematic development since the U-2 shootdown, had proven completely inadequate when confronted with an aircraft that flew fast enough to deny time itself. The laughter that had begun in Moscow in 1960 was dying in the skies over Southeast Asia. And in the classified debriefing rooms of American intelligence agencies, analysts were beginning to understand that they possessed something unprecedented in the history of warfare. A weapons system that could penetrate enemy airspace with absolute impunity, not through stealth or deception, but through the ruthless application of physics to the problem of tactical invulnerability. The enemy could see them coming. They could track them precisely. They could coordinate perfect responses. But they could not touch them. Speed had made the defenders' perfection irrelevant. The reckoning was only beginning. The global implications of what Sullivan had demonstrated over North Vietnam became clear not through dramatic revelations, but through the mundane accumulation of intelligence reports that arrived in Washington throughout the summer of 1967. Each mission added layers to a strategic picture that was reshaping American understanding of Soviet capabilities, Chinese intentions, and global military balance. The aircraft that had been designed to penetrate Soviet airspace was revealing secrets that would determine the trajectory of the Cold War itself. Operation Black Shield, as the Southeast Asian reconnaissance program was designated, completed its first year with statistics that read like the product of military fantasy rather than operational reality. 68 missions had been flown over the most heavily defended airspace in the world. 0 aircraft had been lost to enemy action.
More importantly, 0 missiles had achieved successful intercepts despite hundreds of launches by increasingly sophisticated air
defense systems. But the true measure of the program's impact was found in the intelligence product that flowed from each mission. The cameras carried by the reconnaissance aircraft could photograph individual soldiers on the ground from 17 miles above their heads. Missile sites were catalogued with precision that allowed American analysts to count the number of launch rails installed at each facility. Troop movements were tracked in real time, providing strategic warning of offensive operations weeks before they could be executed. Colonel William Holbury, briefing the National Security Council on the program's achievements, presented intelligence that would have been impossible to obtain through any other means. Gentlemen, we now possess complete and continuously updated intelligence on every strategic target in Southeast Asia. We know the location of every missile site, the deployment schedule of every new air defense system, and the operational status of every enemy airfield. More importantly, we obtain this intelligence with absolute certainty of mission success. The enemy cannot prevent us from observing their activities. The strategic value extended far beyond tactical intelligence. For the first time since the beginning of the Cold War, American planners possessed reliable, real-time intelligence on Soviet military capabilities deployed in a combat environment. The air defense systems protecting North Vietnam represented the most advanced technology available to the Warsaw Pact. Their failure to intercept American reconnaissance aircraft provided definitive proof that Soviet claims of defensive invulnerability were quite simply false. Dr. Albert Whelan, director of the CIA's Office of Scientific Intelligence, outlined the broader implications. The reconnaissance program has provided us with a laboratory for testing Soviet air defense capabilities under combat conditions. We now know with certainty that their most advanced missiles cannot engage targets operating at sustained Mach 3+ speeds at extreme altitude. This knowledge fundamentally alters our assessment of Soviet strategic defense capabilities and, by extension, our understanding of nuclear warfare dynamics. But it was the missions over the Soviet Union itself that would provide the most decisive test of American technological superiority. On March 8, 1968, an aircraft designated Article 131 launched from a base whose location remains classified today, bound for targets that included the Semipalatinsk nuclear test facility and the Baikonur space complex. The pilot's name has never been released, but his mission would prove that the dominance demonstrated over Southeast Asia could be replicated over the most heavily defended targets in the Soviet homeland. The Soviet Union in 1968 possessed the most sophisticated air defense network ever deployed by any nation. Over 3,000 surface-to-air missile launchers protected strategic targets across 11 time zones. Radar installations formed an overlapping network of electronic surveillance that could detect aircraft at ranges exceeding 200 miles. Fighter aircraft maintained continuous combat air patrols over sensitive areas, with pilots trained specifically to intercept high-altitude reconnaissance aircraft. The mission briefing, conducted in a facility whose existence was denied by official sources, outlined the strategic importance of the planned overflight. Gentlemen, Soviet nuclear testing has accelerated dramatically over the past 18 months. Satellite photography suggests the development of weapon systems that could fundamentally alter strategic balance. Your mission is to obtain definitive intelligence on Soviet nuclear capabilities. The photographs you collect will determine American nuclear policy for the next decade. Article 131 penetrated Soviet airspace at 06:23 hours Moscow time, crossing the border at 89,000 feet and Mach 3.35. Soviet radar operators detected the penetration immediately. and the response was overwhelming. Within minutes, over 40 missile batteries were tracking the target. Fighter aircraft launched from 6 different airfields. Air Defense Headquarters activated emergency procedures that treated the incursion as a potential prelude to nuclear attack. General Alexei Yepyshev, commander of Soviet Strategic Air Defense Forces, coordinated the response from his command center beneath Moscow. His forces represented 7 years of systematic improvement since the U-2 shootdown. New missiles with enhanced altitude capabilities, improved radar systems with better tracking resolution, coordination networks that could orchestrate hundreds of simultaneous engagements. The confidence of 1960 had been replaced by systematic professionalism, but the underlying assumption remained unchanged. Sufficient defensive capability could deny any aircraft successful penetration. The results were identical to those achieved over Southeast Asia, but on a scale that removed any doubt about the fundamental futility of the defensive effort. The reconnaissance aircraft crossed 2,400 miles of Soviet territory, photographed 17 strategic installations, and collected intelligence on nuclear facilities that had never been observed by Western sources. 67 missiles were launched during the 4-hour overflight. 0 achieved successful intercepts. Flight logs from the mission, declassified decades later, revealed the routine nature of what should have been the most dangerous reconnaissance mission in aviation history. Multiple launches observed throughout penetration. SAM activity remains below threat threshold. All systems nominal. Photo quality excellent across all target areas. Fuel consumption slightly below planned consumption rate. Weather clear, visibility unlimited. But the true significance of the mission was found not in what the aircraft photographed, but in what it proved about the fundamental mathematics of aerial warfare. Soviet air defense doctrine, refined through years of theoretical study and practical testing, had encountered a problem that no amount of improvement could solve. The enemy aircraft was not hiding from their defenses or evading their weapons. It was simply operating at speeds that made successful interception physically impossible. Marshal Ivan Golikov, reviewing the mission's implications for the Soviet Defense Council, filed a report that acknowledged the magnitude of the problem. American reconnaissance aircraft have demonstrated the ability to penetrate Soviet airspace at will, without regard for defensive measures. Current air defense systems, despite functioning according to design specifications, cannot achieve successful intercepts against targets operating at sustained speeds exceeding Mach 3. This represents a fundamental challenge to strategic defense doctrine. The word fundamental appeared repeatedly in Soviet assessments throughout 1968, always in contexts that suggested problems beyond technological solution. American aircraft had not achieved superiority through incremental improvements or tactical innovations. They had achieved superiority by operating in a flight regime where conventional defenses were irrelevant. The global reconnaissance program that emerged from these early successes represented a transformation of intelligence collection that extended far beyond military applications. The aircraft could monitor compliance with arms control treaties in real time. Nuclear weapons testing could be observed and analyzed within hours of execution. Military deployments could be tracked continuously, providing strategic warning of potential conflicts. Dr. Richard Helms, Director of Central Intelligence, briefing President Johnson on the program's strategic value, presented intelligence capabilities that seem to approach omniscience. Mr. President, we now possess the ability to monitor any activity anywhere on Earth with resolution sufficient to determine strategic intent. Soviet missile deployments, Chinese nuclear testing, Middle Eastern troop movements. All of these can be observed continuously and with certainty. For the first time in the nuclear age, we possess intelligence capabilities that match the scale of modern strategic threats. But perhaps the most important intelligence product was the systematic demolition of Soviet claims regarding their defensive capabilities. Each successful overflight provided additional proof that air defense systems optimized for subsonic threats were helpless against aircraft operating at sustained supersonic speeds. The confidence that had characterized Soviet military planning since 1960 was being systematically destroyed by the accumulation of failures that no amount of tactical improvement could remedy. The industrial statistics that supported the reconnaissance program told their own story of American technological dominance. Each aircraft required 47,000 gallons of specially formulated fuel that cost $4,800 per gallon. Engine overhauls were required every 200 flight hours and involved complete disassembly and replacement of components operating at temperatures that would melt conventional materials. Pilot training required 2 years and included instruction in procedures for flying aircraft that existed at the very edge of the atmosphere. Yet, despite costs that exceeded those of entire conventional air wings, the program achieved mission success rates that approached 100%. Mechanical failures were virtually unknown. Weather delays were minimal due to the aircraft's ability to operate above weather patterns. Mission abort rates were lower than those achieved by conventional transport aircraft operating in peacetime conditions. The reliability achieved through precision manufacturing and systematic engineering was demonstrating that extreme performance and operational reliability were not contradictory objectives. The aircraft that flew at the edge of space were also the most dependable reconnaissance platforms ever deployed. By December 1968, the global reconnaissance program had accumulated over 3,400 hours of operational flight time over denied territory. The intelligence product from these missions filled warehouses and provided strategic assessments that influenced every aspect of American foreign policy. But the most important product was the systematic proof that Soviet defensive capabilities, despite years of improvement and massive resource investment, were inadequate to prevent American reconnaissance aircraft from operating with complete impunity. The enemy could track them perfectly. They could coordinate flawless responses. They could expend unlimited resources in pursuit of successful intercepts. But they could not achieve the only result that mattered: denying American aircraft access to Soviet airspace. Speed had accomplished what secrecy, stealth, and tactical innovation could not. It had made enemy defenses irrelevant through the simple expedient of operating faster than defensive systems could respond. The mathematics of interception, so favorable to defenders in 1960, had been rendered meaningless by aircraft that denied time itself to their adversaries. The global map was being redrawn, not through conquest or diplomacy, but through the systematic collection of intelligence that revealed the true capabilities of every major military power. And in Moscow, the implications were becoming clear. The sky belonged to whoever could fly fast enough to deny it to everyone else. The verdict was approaching, and it would be delivered not through dramatic confrontation, but through the quiet accumulation of evidence that Soviet claims of defensive superiority were, quite simply, false.